Okay, 2, 4, 6. So other things should be deleted. This 1, 2, 3, 4. Here also if you take 3, 4, 5, 6. Here also if you take 5, 6, 7, 8. So what we need is this 1 should be deleted, then 3 should be deleted. Here also 1 should be deleted and 3 should be deleted. Here if you take 3 should be deleted, 5, 6 should be deleted. 3 should be deleted, and because they are restrained, there is no degree of freedom. So whatever is restrained, you have to strike it off. So the remaining values only you will take. If you take this one, you will get the 4 4 value. All the other strings 4 4, and this also will get 2 4, then this also will get. So finally we will get a matrix. uh, 2 4 6. All the other things will go off because they are restrained. 1 is restrained, 3 is restrained, vertical displacement restrained, 5 is restrained, 7 8. This is a fixed end, so rotation is restrained and vertical translation is also restrained. So you will have finally only rotation at this end, rotation at this end, and rotation at this end. So finally you will have only this one, 2 4 6. So I'll rub it off. Other things will go off because they are restrained. If you want, you can keep like that, but the simultaneous equation you have to solve is will be more. So in order to cut short the procedure, that is simplify the number of equations, you are going for this one. So that's the thing. Now finally what we need is 2 4 6. So other things should be thrown off. 2 4 6. So this particular program will give us how to incorporate only. So you will have a sum of the first number. If you take a sum of 2 comma 2, that is this value you will have. Then 2 comma 4 you will have, 2 comma 6 you will have, then the 4 comma 2, 4 comma 4th row, 4th column, then 4th row, 6th column, 6th row, 2nd column, 6th row, 4th column, 6th row, 6th column. Okay, 6 columns is this numbering. Actually it is 1 2 3, so you will have this numbering. So we will check. We have given a new ID. Am I correct? 2 has become 1, 4 has become 2, and the 6 has become 3. So here also it has become 1 2 3. So last class we have seen how to change the ID for this one, the 2 4 and 6. We have seen the last class programming. So this is this one. So let us look at the first line. Im of 1 is equal to 2 into jj of 1. Can somebody tell me the value of jj of 1? That is jj of 1 is equal to, look at your note and tell me. jj of 1 is equal to, what is the value? 1 minute. I will put 1 1 1 1 1. Okay. jj of I, sorry, jj not jj of I. Here the member is, let us take the first member is being executed now. The first member, that it is taking care of the first member. So first member is this one. So first member means I becomes 1. That is in the previous slide we have seen, no, the member will it will be coming from 0 to, for I is equal to 1 to m, 1 to m. So the member will, now it will become 1. So for the first member, all the activities will be done. That is the first it has calculated this values, everything is over. Now we have to move on to the second member, that is jj of I. jj of I is equal to 1. So jj of I is equal to 1. So can you calculate and tell me 2 into 1 minus 1 is equal to how much? 1. Am I correct? 1. Then Im of 2 you calculate, 2 into 1. 2 into 1 is equal to 2. Then this line, what is jk of 1? jk of 1, 2 into, somebody can tell me, jk of 1 is equal to 2. 2 into minus 1, 4 minus 1 is equal to 3. So 1 2 3, 1 2 3. Then Im of 4 is equal to 2 into jk of 1. Can you tell me jk of 1? Jk of 1 is equal to 2. So that is equal to 4. So it has become 1, 2, 3, 4. So whatever is I'm doing for the first member. So once the first member is over, then it will move on to the second member because it has to pick up the value based on some conditions, whether this should be included or not in the global. So whatever I'm discussing is about the global stiffness matrix. So it has to, computer has to throw off some of the values and some values should be taken. Global stiffness matrix. Global stiffness matrix. So this is okay. So for it has to do for one j is into 1 to md. Can you tell me the value of md? Already we have calculated. What is md? What is md? Here we have seen no md is equal to member displacement. Number of degrees ndj into 2. So it is 4. Am I correct? Member displacement. 4. Yeah, member displacement is 4. So for a beam, that is for the sake of Gibby and Thamari Selvan, I will explain just now. That is MD represents if you take this member 1, this is 1 and this is 2, this is 3, this is 4. So it has got a vertical translation rotation. So MD in a member has 4 possible displacements. 4 possible displacement. So possible is different from the available actual displacement. So possible means it can be 1 and 2 can be restrained or it can be free also. Suppose if I am taking this, it's a fixed support, then 1 and 2 are restrained. It is not free to move. So the possible displacement is, so it has to be done from 1 is to 4. So I1 is equal to, now I1 is equal to Im of j. Im of j means j has become 1. That is j will become 1 now. That is I1 is equal to Im. What is Im of 1 now? Im of 1 is equal to 1. Am I correct? So it will look for the previous line. Previous line is stored. Im of 1 is equal to j has become 1. So what is the notation? 1 minute. So this is, we have seen 1, this is 2, this is 3, this is 4. So j has become now 1. So Im of 1 is equal to, Im of 1 is equal to, I1 is equal to Im of j. J means Im of 1. Im of 1 is equal to 1. I1 is equal to 1. Similarly, there is one for loop here. That is, this for loop is, let us take this one. Then there is one inner loop also. That is, this is up to this one. This is up to this one. And there is one more inner loop. This is up to this one. There is one more if statement. So that will be up to this one. So like that only it will calculate. So well, let us take the outer for loop. Outer for loop will go up to here. J is equal to 1. I1 is equal to Im of j. I1 is equal to 1. For k is equal to 1 to empty. K is equal to 1d empty. That is, now k has become 1. So it is I2 is equal to, so the computer will take one by one step. That is, it will go to the first step, second step, third step, like that it will go. So I2 is equal to Im of k. K is equal to 1. What is Im of 1? Im of 1 is equal to 1. Im of 1 is equal to 1. So now there is a check. If JR, if JRL of, what is that? I1 is equal to 0 and JRL of I2 is equal to 0, then what is that? ID. You have to give a check for ID whether you have to incorporate in the global stiffness matrix or not. So JRL of, just 1 minute. So JRL of I1, JRL of I1, JRL of I1 means there is a check if. So JRL of I1 means JRL of I1 has become, now what is the value of I1 now? We have seen I1 is equal to 1. JRL of I1 is equal to 0 and JRL of I2 has become 1. I2 has become 1. I1 has become 1. So I2 is equal to 1 is equal to 0. Whether it is correct or not, this sentence is correct or not, JRL of both the things should be 0. Whether it is what is JRL of 1? What is JRL of 1? John Dresden. Somebody can answer me? No, we have seen. What is JRL of 1? JRL of 1 is equal to 1. Am I correct? Is it true? JRL of 1 is not equal to, if it is equal to 0, if this condition is satisfied, then you have to go for the next step. If it is not satisfied, then you have to throw it off. So if it is satisfied, JRL of 1 is equal to 0, then you take into account of that. So this condition is not satisfied. Am I correct? What is JRL of 1? JRL of 1 is equal to 1. That is what we have seen in the previous steps. That is here, see here. JR of 1. So this condition is not satisfied. No, both the conditions should be satisfied. If any one of the condition is not satisfied, the condition means there are two conditions. One is JRL of I1 should be equal to 0. Second condition is JRL of I2 should be equal to 0. But if any one of the condition is not satisfied, then it will not be executed. So this, if you take this one, then it is not getting satisfied. So what will happen? It will not be taken into account here. It will not be taken into account. If you take JRL of, if you take, let us take this one, JRL of 2, 2. What is JRL of 2, 2? JRL of 2 is 0. So what will happen? JRL of 2 is 0. Then it will take the ID of I1. What is ID of I1? ID of I1 means we have calculated yesterday. No, ID of I1. Sorry. This place. Here we go. ID of I1. It will take ID of I1. It will take and it will assign. So it will check whether I should incorporate or not by this condition. So if it is incorporated, then it will by this statement it will incorporate and keep it. So when you come to the first, it will finish for the first member. Let us take for the first member the stiffness matrix. The 2 2's, we will consider this 2 2 alone. 2 4 6 2 4 6. We will consider this one. The first member also you have 2 4. The first member also you have. When you number it, you will have 1 2 3 4 5 6 like that. So first member only you will have 2. Second member, the common thing is 4. So when you come this one, it will for the first member also you will have 4 2. The second member also you will have 4 sorry, you will not have 4 4. You will have 4 4. Second member, because the 4 is common for the first member. The connectivity for the first member is 1 2. The connectivity is 1 and 2, 3, 4 like that. So this 2 is common for the first member and the second member. So this 4 will be there for the first member and the second member. So this is something will be added. So that action will be taken by this one. Do you understand? So what you have to understand is, first we are calculating this something we are doing, initialization we are doing, and by this by doing this one you will get the 1 2 3 4. So you have to calculate from, it's a 3 by 3 matrix. So it will calculate from, it will check for all the displacements. What is whether I should initially it is actually truly speaking it will be a 8 by 8 matrix. Am I correct? 1 2 3 4 5 6 7 8. So but some of the things are we have to neglect. We have to, 1 is neglect, 2 3 neglect, 5 neglect, and 7 also neglected, and 8 also neglected. So only remaining thing is 2 4 6 because only rotation is there. So this only you have to put it in the final form. This is a formulation of the global stiffness matrix. If you want, you can try for the next set because it will take time. I'm just skipping. This is a basic of that, and how it is being identified. So the thing is identified by this check. If JRL of 1 is equal to this is satisfied and this is satisfied, then I should add here. That is the criteria. Otherwise, I should not ask that. So, for example, I told JRL of 1 is equal to 1, so it is not satisfied. So, 1 comma 1 should be thrown off. It should be thrown off. It should not be added here. The computer will not consider. When you go to 2 comma 2, it will add like that. One by one, it will check away. Then it will become, the J will become 2, and here it will, J will become 1 and K will become 2. Like that, it will move on. That is, for example, I'll switch off this one. Discard. I'll just explain this one alone and I'll leave and I will start the second unit. That is, it has to start from 1. It has to go from 1, 2, 3, 4, and here also it has to go from 1, 2, 3, 4 for the first member. So first it will look for the outer loop. Outer loop it will be remaining as 1. So 1, and the inner loop it will be increment as 1, 2, 3. So what you will get is 1 comma 1. The next one is 1 comma. This is always 1. So outer loop will remain 1 and the inner loop will be completed up to 4. 1 comma 2. Then you will get 1 comma 3. Then you will get 1 comma 4. So the first row will be completed. So when the first row is completed, then it will move to the 2, the second row. So MD will become 2 now. So 2 comma 1, 2 comma 2, 2 comma 3, 2 comma 4. Like that it will go. So it will go 3 comma 1 and 4 comma 1. Like that it will be completed. Can you just copy down? So I think I will finish it. How to formulate the stiffness matter. That's enough. That is the concept. If you understand, this is enough for your programming. So this can be applied to the what is that frame structure also. I'll tell you where you have to do the modification. Can you just copy down this? You finished, tell me. Have you finished? Somebody can answer me. Have you finished?
Yes, ma'am.
So with that, I'll move on to the third unit because we have to finish the portion quickly. So this and all, if you take, I'll just tell the frame. What is the difference in the program technique for the frame analysis? Degree of freedom of a joint. This will become 3. That no, because we know, because if it's a beam, degree of NDJ we will become. This is if it's a beam, how we number. This is 1 and 2. Suppose if it's a porta frame, the same hinge we will number as horizontal is 1, this is 2, this is 2 and rotation is 3. So the NDJ will be equal to 3. So this is number of degrees of freedom for a member is equal to joint is equal to 3. Number of degrees of freedom for a joint is equal to 3. Here it is a beam, it is 2. That's the difference. Then other things will be same because I have the program is developed in such a way that it can be used for the beam and the column and the port of 2D frame, and remaining things are same. These are the length of the member, everything is same, and where you have to, these are all same. Only the stiffness matrix, it will be different. The stiffness matrix, what I will suggest the students is stiffness matrix is R transpose element stiffness matrix. KE is equal to R transpose KR. So what I will tell the students is you have to cast if you take the rotation matrix, R matrix, you will have cos theta, sin theta, 0, 0 like that. You will have value, and minus sin theta, cos theta, you have 0, 0 like that value. You have value. So then you will have, if you first you take the KR, then you will have AE by L. AE by L, 0 minus AE by, like that you have values, and you have to make it as a simple line. That is, you have to multiply the first row and the first column, you multiply final product, that should be multiplied or transpose, and finally you will get one term. That term should be supplied here. That is, instead of the very only 12A by L cube, you will have some cos theta and sin theta terms. So that you will, if you want, I'll send the program to you in the subsequent classes. So that is this is a change you have to make it, and this will become, instead of 4 by 4 matrix, it will become 6 by matrix, 6 by 6, 1 2 3 4 5 6. So that's the difference. So this stiffness matrix alone will change, other things are common only. So you need not worry about that part. I will if you want, I'll give you the program in the next class. Okay, so today anyway we have to start the first unit. Sorry, third unit. We have to start this third unit. What I'm doing is, third unit is I'll just show the can you just take down the syllabus portion? You may be having, but just you take a note of this one. This is mathematical foundations of this is the introduction principle only. That module 3 is simple when compared to the other modules. This is very simple, and the fourth and fifth are little bit tougher than when compared to the third module. This is something. What is that? The theory part and some introduction of that. Can you just note down the syllabus? Mathematical foundation of finite element method, so that you can have some concept of what you're going to learn. Historical background.
Yes, ma'am.
Okay, so done it. Finished. Okay. Now I am going to give some video which will cover up to what is the concept of finite element and the derivation of elements up to this one. That is a characterization of 1D, 3D problem. Up to this one it will cover, and some part of the stress strain equilibrium equation also. Then and there I'll stop playing the video. First thing is the historical background, how it is being developed, what is the meaning of continuum. Then and there I'll stop it and I'll explain it because it is a little bit faster for you to understand. So wherever it's needed, I'll stop and I'll explain you. So just tell me whether you are able to hear the sound of this video. Are you able to hear the sound volume?
Right, ma'am.
No, ma'am.
No,
ma'am.
yes or
Yes,
no?
ma'am.
Yes,
Right,
sir.
ma'am.
Yeah, you are able to hear the voice sound.
No, ma'am. No, ma'am.
I'm not able to hear you.
No.
Yes or no? No.
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 Wait, that I'll once again play. Now you tell me.
How it all began. Then we will jump to what the finite element method is. How do we use it? How does it help us? What is the
Yes,
so-called
ma'am.
divide and conquer approach? We will
Yes or no?
Yeah, no, it's visible, ma'am.
Yes,
Yeah,
ma'am.
audible, ma'am.
Audible. Okay.
mathematically derive the equations for the finite element method.
1 minute, I'll replay.
Hey friends, and welcome back to my channel. In today's video, I want to give you a brief introduction to the finite element method and not delve too much into mathematical operators and formulas, but keep it very simple. So let's jump right into the agenda. I want to give you a brief overview of the historical background of the finite element method and how it all began. Then we will jump to what the finite element method is, how do we use it, and how does it help us, what is the so-called divide and conquer approach.
Can you just copy down what we are going to deal today so that you can have a feel of what you are hearing? Historical background, everything is in your syllabus. What is historical background? What is the finite element method? And why do we use it? And how to divide it? What is the approach for that? And the derivation of finite element method, and what is the meaning of form, boundary condition, and the element type. Just to note down what you are going to learn. So then and there I'll stop and I'll make you to write it because it is in our syllabus only. So finished?
We will mathematically derive the equations for the finite element method and talk about boundary conditions. Last but not least, we will talk briefly about element types. So basically all began with the so-called Baristo-Chrome problem with Galilei in 1638. And he mentioned in his last work that the sphere will go faster.
So first what he is explaining how the finite element method is being developed. That is the background, historical background of the development of the finite element method. This and all you just listen, but you need not note down any way, but I'll give you the link for that, and just you can listen and you need not note down.
From A to B following a curvature, which is under the effect of gravity. Then Bernoulli came in 1696, who was one of the fathers of variational calculus, and he presented this problem in his 15th version in Leipzig, in the so-called Acta Eruditorum. And this was one of the first scientific journals ever. And he tackled this problem because he was a little bit into competition with his brother Jacob. In 1697, we have Leibniz coming up with his first draft of a discrete variational method with element-wise triangular shape functions. We will discuss shape functions in a future video and not delve too much into shape functions in this basic introduction. Lagrange, 1755, who laid a solid foundation for the finite element method, where he basically took an optimal solution, perturbed it by an arbitrary variation, and called it delta y, which we later on called test function. Schellbach came in 1851 with some analytical studies on this variational problem or problems. Then Rayleigh followed 1877, who did some numerical analysis on these problems. We have Ritz coming up in 1908, who proposes and analyzes approximate solution based on linear combinations of simple functions. And he solves two difficult problems of his time. He solved the linear elastic Kirchhoff plate problem with a variational method, and the main motivation of Ritz at that time was the announcement of the Prix Vaillant 1907 by the Academy of Science in Paris. Courant in 1943 introduced triangular and rectangular finite elements for the 2D Saint-Venant torsion problem. So jumping to 1956, we have the first finite element paper released by Turner, Clough, Martin, and Topp. And in case you want to have a look at that, you can see the title in the bottom right corner. In 1965, we had the NASA project, and they issued a request to start a development for a structural analysis tool, which we call Nastran. Some of you might know it. It's very famous. 2 years later, the first FEM book was released by Dr. Zienkiewicz, and he simply called it the finite element method. In 1968, we have the term isoparametric mapping popping up. So Zienkiewicz and some colleagues introduced isoparametric mapping for quadrilateral elements. This will also be covered in a future video and not discussed in this basic introduction. In 1970, people could combine 1D and 3D theory in the same mathematical modeling. 2 years later, we have the first mathematical paper on the finite element method by Babushka and Aziz. And beforehand, no uniqueness and convergence has been proven so far. And on the right-hand side, you can see one of the fathers of the finite element method, the famous Gilbert Strang. 5 years later, we have the first professional finite element P-version code called Fiesta. 5 years later, a P-version FEA software tool called Probe for aerospace applications was developed. 1991, people were discussing and developing model hierarchies, where we have separate arrows of discretization and idealization, which is basically essential for verification and the validation, as well as the uncertainty quantification. And we have a finite element book as well coming out from Jabot and Babushka. We jump right to 2006, where the American Society of Mechanical Engineers released a guide for verification and validation in computational solid mechanics.
Tried using rich chemical products. Now the time is to get back to Ayurveda.
2 years later, NASA released a standard for models and simulation. This standard consisted of 2 parts, and you can read a bit about it by pausing the video or simply downloading the slides. And in 2013, we have the world's first cloud-based simulation platform called SimScale. So what is the finite element method? Some of you might have heard this term before, or other terms like finite volume method, finite difference method, as well as spectral method. These are all computational methods or techniques developed by engineers to solve a problem, but always in an approximate method.
Can you just write down what is the meaning of finite element method? Finite element method is a computation method developed by the engineers to use to obtain approximate solution. So this is very important. That is, it's not a correct solution. So it's an approximate solution
manner. So this is a model.
So this is an approximate solution. It's not a it's a numerical method. It's not an analytical method. So analytical method you will get the exact values, but in this case, numerical methods are you will get the approximate solution close away. For example, if the deflection is equal to 0.9 mm, by this finite element method, you may get 0.88 mm, 0.8 mm. The error is 0.02 mm. So 0.02 mm, if you want to get accurate solution, then you have to reduce the size of the meshes, and you have to do some you have to repeat the procedure. You have to do it again and again, and till you get the exact solution, you have to do it. So as I told, if it's a deflection of a beam is 0.9 mm, by the finite element you may get 0.88 mm. That is, the error is 0.02 mm. So it's an approximate solution. Can you just note down what is finite element method? The answer for this, you can note it down.
Yes, ma'am.
Okay.
And we want to approximate the real world by using these models or these methods or techniques. Nature can usually be described by partial differential equations, short PDEs, and nature is continuous. So we have an infinite number of degrees of freedom, and we want to make it discrete. We want to have a finite amount of values that we know and that we can actually solve. So we go from the partial differential equations to the system of linear equations which our computer can solve. And with today's power available, we can solve very large systems. Please note that this is always an iterative process. I will talk.
So it is a that it requires a large amount of computational power, and very large linear systems of equations can be solved. So we'll be using instead of partial differential equations, it will be converted into linear equations, and you will be. What is the difference between the linear means? I think you will understand for example, if you take it y is equal to mx plus c, that's the equation of a straight line, that's a linear equation. So like that, so iterative process, by doing the iterative process, you can get the nearly exact solution. So can you just note down this also? So partial differential equations, dou square y by dou x square. So that's a equation. So you can get the exact solution by the iterative process only. I think the time over. No, for you it is 11:55 to 12:45. No, this hour. Am I correct?
Yes, ma'am.
Okay. I don't want to disturb you. So I'll stop with that one. Just copy down, and I'll stop with that.
Okay.
Okay.
Copy, ma'am.